In the previous video we looked at black body radiation, and in this video we're going to take that further and identify how that helped us to develop our understanding of light. You can see the three dot points that are highlighted there, and you'll notice that they all refer to energy and photons. So we'll have a look at what that means in this video and identify how it was that this idea of a photon came about. So as we mentioned in the previous video, there was a discrepancy between the prediction of black body radiation and the actual observation of black body radiation itself. So that discrepancy was that there was a difference in the energy at high frequencies or at short wavelengths, and where the prediction was that the energy should be quite high at short wavelengths, but the actual observation was that the energies were low. The solution to that was developed by Max Planck, and in coming up with this solution, it's interesting to note that he actually didn't think it had any physical meaning. He thought it was literally just a mathematical solution to this problem, and in proposing that mathematical solution, it wasn't until Einstein came along and applied it to an experiment that we'll see in the next video that it was able to be shown that this wasn't just a mathematical solution, that it did actually have some physical meaning. And that solution was that instead of treating energy as being radiated continuously, he treated it as being in quantized packets. So the wave model predicted that energy would be given off continuously, so as a continuous variable. Instead, his mathematical solution was that it was radiated in quantized amounts. Now that word quantized is where we get the term quantum theory. So by quantized, what we really mean is that it's discrete. So instead of it being a continuous spread of energy, it's actually radiated in discrete packets. So discrete packets of energy. Now that idea of a discrete packet of energy, or a quantized packet of energy, is what we now refer to as a photon. So the term photon was more developed once Einstein started to apply this solution, but we'll deal with that in more detail in the next video, as I said. Now the idea then of a photon, if it's going to carry energy, there must be some way to calculate how much energy it has. That calculation links into Planck's solution, but we're not going to go into the full detail of that solution. It's a fairly complex one. Instead, all we need to be aware of is the end point of it, is that the energy of the photon is given by this equation, E is equal to hf, which is in the data booklet. And again, to outline what the variables are, E is the energy of the photon, and as we know, energy is measured in joules. F is the frequency of the electromagnetic wave. Note that we're now linking waves with energy, and if we're dealing with a frequency, it's going to be measured in hertz, and the final value there, h, is known as Planck's constant. Now Planck's constant is a fairly important one. It's one of the fundamental constants of the universe, and we'll do a couple of demonstrations in class later where we actually go through and calculate Planck's constant. The value of Planck's constant is 6.626 by 10 to the negative 34, and the units are joules seconds. And again, that's another quantity that's given to you in the data booklet. So there's the equation that relates to photon energy. We'll have a look at an example of how that can be applied. And so, a fairly simple example, calculating the energy of a photon of laser light, with a wavelength of 650 nanometers. So the first thing here, note that we've got the wavelength, not the frequency of that photon. So we need to go back to the wave equation. So V is equal to F lambda is the equation we need to refer to. But here we're dealing with electromagnetic waves, and so the speed is actually going to be the speed of light c. So that's going to be equal to F lambda. From there we need to figure out the frequency, so we can identify that F is equal to c over lambda. Now rather than calculating that value, I'm instead just going to substitute it straight into the equation. E is equal to HF. So instead of F, we're now going to write this expression for F being c on lambda. So there's an alternative form of the equation to calculate the energy. So now we have that the value of Planck's constant, 6.626 by 10 to the negative 34. We need to multiply that by the speed of light, 3.0 by 10 to the 8, another value that's in the data booklet as we've already discussed, divided by the wavelength, so it's 650 nanometers, and nano means by 10 to the negative 9. So when you go through and do that calculation, you find that the value then is 3.06 by 10 to the negative 19 joules. So you can see there that the energy of a single photon is really quite small. And because photon energies are quite small, we won't always write the energies in joules. There's another unit that we've already covered back in Unit 1, where we looked at how we can quantify energies when the units are quite small. And the reason why the units are quite small here is the value of Planck's constant being in the order of 10 to the negative 34. So we're always going to find that photon energies are really quite small. And so an alternative unit is used, and that unit is the electron volt. So the definition of an electron volt is that it is the energy required to move an electron through a potential difference of 1 volt. So note here it's about energy, it's not a voltage, so even though it's got the term volt in it, don't be confused by that. An electron volt is a unit of energy. And hopefully you can find in the data booklet that 1 electron volt is equal to 1.60 by 10 to the negative 19 joules. So as I said, that is in the data booklet, so I'll just highlight that. And that then means that from the previous example, so the photon energy from that question that we just did before, so from the red laser, had an energy of 3.06 by 10 to the negative 19 joules. If we want to convert that then to electron volts, we'd need to divide by that conversion factor. So divide by 1.60 by 10 to the negative 19, and that gives us a value of 1.91 electron volts. In the next video we'll start to apply the understanding of photons to the photoelectric effect, and that's the experiment for which Einstein won his Nobel Prize in 1905.